In this video, we are going to start the process of talking about how do we estimate some kind of parameter. And we're going to start with the proportion. Anytime you hear the word estimate, that means that we're talking about confidence intervals. So it's your key for that. If you remember, back a few videos ago, we talked about good point estimates, what were good unbiased estimators of population parameters. And one of those was the proportion. We said that the sample proportion tends to target the population proportion. So a point estimate, anytime you see that, it's really just the value of a statistic that estimates the value of a parameter. Um, And the ones that we saw were unbiased estimators were the proportion and the mean. And we also saw variance. And we're really going to focus on the proportion and the mean. So the point estimate for the population proportion is the sample proportion. And this is the notation that I'm going to use in my videos for sample proportion. It's going to be a P with a little caret key over it. That's pronounced P hat. Looks like the P is wearing a little hat. And it's going to be the number of successes divided by the total number. So when we talk about a confidence interval, we are trying to get some kind of range of values where we think that population parameter, in this case, we're going to focus on the proportion, is going to live. The level of confidence that's associated with that represents the expected proportion of intervals that will contain the parameter if a large number of different samples is obtained. Usually we talk about confidence intervals like we want to be 95% or we want to be 99%. So, for example, if we have a 95% level of confidence, then our alpha is the complement of that. And that would be the complement of 95, which is 5%, which we could write as a decimal as 0.05. You always see alpha written in terms of a decimal. And what that means is suppose we were going to have 100 different confidence intervals that's constructed. If we were 95% confident, then that means that 95 of those 100 intervals would have that true population parameter. So a lot of times you're not going to know what the population parameter is. I mean, if we're talking about a confidence interval for the proportion of people who are going to vote in the next election, we would be talking about all American citizens who are eligible to vote, and that's millions of people. So it's not really likely we're going to be able to get um, a census, collect data from everyone in that population. So that's where samples come in. We could get a good sample, not a convenient sample, but more like a random sample or simple random sample. And then um, we could run some statistics on that to determine things like what would be the percentage of people we would expect to vote in the next election. So, how do we go about doing that? Well, we're going to use that point estimate, which in this case is going to be our p hat, and then we're going to add and subtract the margin of error. And we're going to find the margin of error using a formula here. And that margin of error is also called standard error. I'll use this. Equals the square root of p times 1 minus p divided by n. So I'm going to find this number, and I'm going to take p hat, add and subtract that number. And when I take p hat and subtract that number, I'm going to get a lower bound. When I take p hat and add that number, I'm going to get an upper bound. So then we could be 95% confident that the true population parameter would live between the lower bound and the upper bound. And that's our goal, is to figure out where would it live. Now, there's some criteria that has to be met. So these are your must-haves. her criteria. First, the shape of the distribution of all possible sample proportions has to be approximately normal. And we could test that by looking at n times p times 1 minus p and see if that's going to be greater than or equal to 10. And we want the sample size to be no more than 5% of the population mean. Secondly, the mean of the distribution of the sample proportion has to equal the population proportion. And then third, we've got that standard error that we're going to find. Interpretation. So some kind of confidence interval, let's say we're looking at a 99% confidence interval, means that if we were to construct 100 intervals, I'll use CI for confidence intervals here. Let me clean up my notes. So if we were to construct 100 confidence intervals, then we would expect, if we want to be 99% confident, we would expect 99 of those confidence intervals to contain that true population proportion. Okay, so let's talk about what that sentence would mean and what it would not mean. So extremely important point is that the level of confidence refers to the confidence in the method and not in the specific interval. And now we're talking about 90%. A 90% confidence interval means that the method works. That is, the interval includes the unknown parameter for 90% of all samples. So if we were looking at a 90% confidence interval and we were to construct 100 samples, we would expect 90 of them to have that true population proportion. We do not know whether a particular sample statistic obtained is one of the 90% with the interval that includes the parameter, or if one is 10% of whose interval does not include the parameter. And that's because it's virtually impossible to get that population parameter and to collect data from everyone in the population because our populations tend to be so big. A 90% level of confidence does not tell us there is a 90% probability that the parameter lies between the lower and the upper bound. Okay, it refers to the method, not to a percentage of probability. So if we wanted to look at a blanket statement for a population confidence interval, we would say, or estimating population confidence interval, we would say we are some kind of percent confident that the true population. So we're in this class, we're going to talk about the mean or the proportion. So you would choose the one that you're talking about. Is between. And this is going to be your lower bound. And this is going to be your upper bound. So there's a statement that you could use to summarize what you found. So let's look at a few examples. We want to construct some confidence intervals. So our lower bound is going to be p hat minus the error. Upper bound is p hat plus the error. Okay, notice we're going to have to find a z-score that's associated with that. And we're going to have alpha over 2. So if we're looking at being 95% confident, our alpha is the complement of that, which is 5%, which is 0.05. So when I look at z alpha over 2, I'm looking at z of 0.05 over 2. And what that means is I am taking that 5% and I'm splitting it between the tails, and I'm doing that evenly. So I'm really looking at z of 0.025. I have an area of 0.025 in the left tail and in the right tail. So if I wanted to find the z-score associated with that, I could go back to using my technology. So I'm looking at a normal distribution. This is the standard normal. So the mean is 0 and the standard deviation is 1. We know that probability in that right tail is 1.9, is 0.025. So if I type that in here, hit enter, it's going to tell me what that z-score is, which is going to be 1.96. So if this side is 1.96, then this side over here would be negative 1.96 because of the symmetry that's associated with that normal distribution. So our margin of error is going to be z alpha over 2 times the square root of p hat times 1 minus p hat divided by n. This is our formula for the error, and I made a mistake earlier when I called this the error. This is not the error. This is the standard deviation of the sample proportion, of the distribution of the sample portion. So I apologize for that error. Now, if we needed a sample size for estimating a population proportion, we could take this and we could solve it for n. We could divide the error by this number. We could square both sides, which would get rid of the square root. And then we could flip both sides of the equation. As long as you do the same thing to both sides, it's a legal move of math. It would be the same thing as doing a cross multiplying and solving type thing. And then we can multiply both sides by this denominator. And that would solve that for n. So that's where that formula is coming from. It's taking this guy and it is solving it for n. Because, maybe we know what we want the error to be. We don't want to be any more than maybe 2 percentage points either way. Then what would our n have to be? So we're going to use this formula if we know p hat. If we don't know p hat, we're going to use this one. Okay, so what's happening with this one is that they're replacing that p hat times 1 minus p hat with 0.25. So they're making the assumption that p hat is equal to a half and its complement, so 1 minus p hat, would also be equal to a half. So we're going to have the same chance of those happening. And then if I multiply a half times a half, I get 0.25. So that's where the formula is coming from there. All right, so let's look at a few examples. This one, we want to determine the critical value that's associated with a given level of confidence. So for 90%, we're looking at alpha as 0.10. So we're going to draw a picture. We're looking for z alpha over 2. That's going to be our critical value. So we're going to take that 10% and split it between the two tails. So we're going to have 5% in each tail. So we're going to have z of 0.10 over 2, which is z of 0.05. And if we use our technology, we're going to get that 1.645 again. We get the same thing over here. Alpha is going to be 1%, which is 0.01. We're splitting that 1% between each tail. So we're going to get 0.005 in each tail. And when we talk about that critical value, we really only care about the positive ones in this case. When we start talking about t-distributions, it's going to be a little bit different. And we're going to get 2.58 for that critical value. So let's look at some other problems. In this, they're giving us the lower bound and the upper bound for a confidence interval, and they're asking us for the p-hat, which is the point estimate, determine the point estimate, and the margin of error. All right, so if we have the upper and lower bounds, this is going to be really easy for us to figure out. P-hat has to be in the middle. So if we take the upper bound plus the lower bound and we divide it by 2, that's going to tell us exactly what's in the middle of the bounds. So we'll look at number 11. So we're going to take that upper bound plus the lower bound, and we're going to divide it by 2. And when we do that, I get 0.225. So there's my p-hat. Now the error is going to be the difference divided by 2. So upper bound minus lower bound divided by 2. So 0.249 minus 0.201, and we're going to divide that by 2. And when I do that, I get 0.024. Okay, if you wanted to check it, you could. Remember, it's p-hat plus or minus the error. So if I take this and I subtract that error, I'll get that lower bound. And if I take this and I add the error, I'll get that upper bound. So now let's look at finding one. Let's look at number 15. They want us to construct a confidence interval. So they're telling us x is 30, n is 150. So our p-hat value is going to be x divided by n. It's the number of successes divided by the total. So I'm going to get 30 over 50, which is going to be 0.2. This is a nice decimal, so I'm going to use a decimal there. So next, let's figure out our error. Our error is going to be z alpha over 2 square root p-hat 1 minus p-hat divided by n. So I got to figure out that z alpha over 2. So it's going to be z of, now in this case our alpha is 10%. So if I take 10% and I divide it by 2, I'm going to get 0.05. So I'm going to replace this with 0.05. P-hat is 0.2, 1 minus p-hat divided by n. We could use our technology to find z of 0.05. And that's going to be the 1.645. So we get 0.2 times 0.8 divided by 150. And I'm going to type this in my calculator off screen. So I got 1.645 square root 0.2 times 0.8. All that's divided by 150. So I got an error of about 0.054. So if I take my p hat and I add and subtract my error, that's 0.2 plus or minus 0.054. So if I take 0.2 and subtract 0.054, I'm going to get 0.146. So there's my lower bound. If I take p hat 0.2 and add 0.054, I'm going to get 0.254. So there's my confidence interval. So now I'm going to show you how to use our SALT tool to figure that out. So under SALT, you're going to choose inferential statistics, and you've got a lot of drop-down options here. We're doing a one sample proportion. It's going to ask us for the number of successes. In this case, it was 30. Trials is 150, and we are doing a confidence interval. And then it asks for that confidence interval. In this case, it's 90%. And when I click generate, it will tell me my lower bound and it will tell me my upper bound. So it gives us everything that we had over here. Okay, so let's use technology to do number 16. So we're going to type this information in. So one sample proportion. 16 says X is 80. Number of trials was 200. We want to be 98% confident. So we're going to generate some results. And we've got a lower bound and an upper bound here. All right, so I'm going to write those on our notes. So my confidence interval, I'll write it this way, is between 0.319 and 0.481. Just double check that. So if we wanted to know p hat, we could take upper plus lower divided by 2. We're going to get 0.4. And if I wanted the error, it's going to be upper minus the lower divided by 2. So if we wanted to write a sentence that summarized everything, we could say we are 98% confident that the true population proportion is between 0.319 and 0.481. So let's do one more example. So we have a survey of 2,306 adults age 18 and older, found that 417 have donated blood in the past 2 years. A is asking us for a point estimate. So the point estimate is going to be that sample proportion, which is going to be 417 out of 2306. So 417 out of 2306, that is not a nice number. It's about 0.1808. B is asking us to verify that the requirements are met. So that's where we would check N times P hat times 1 minus P hat. So our N is 2306. Our P hat is 0.18. We'll go 181. We'll round that to 3 decimal places. and then 1 minus p hat. And if we were to type that in our calculator, I get 341, which is definitely bigger than or equal to 10. So that requirement is met. And the samples definitely is less than 5% of the population. We're talking about adult Americans age 18 and older. There's millions of them, and we're only looking at a sample of 2,300. So C is asking us to construct a 90% confidence interval. So we're going to use technology to do that. So we're going to go back to SALT. 1 sample proportion. The number of successes is 417. The number of trials is 2306. Confidence interval, and we want to be 90%. So our confidence level limits are 0.168 and 0.194. So the D is asking us to interpret. So this is where we would write a sentence. So we would say we are 90% confident that the true proportion, I'm going to abbreviate that, of adult Americans that have donated blood in the past 2 years is between, I'm going to turn these into percentages, 16.8% and 19.4%. We could also leave them as decimals. Either one would be fine. But do you see how we took that interpretation and we made it very specific to the problem that we're talking about? That is our point in doing that interpretation.